So in this video, I'll cover about the concept of traveling salesperson problem using the dynamic programming. So traveling salesperson indicates, that is in brief, what is actually the traveling salesperson problem. That is, we need to start from the source vertex and reach all other vertices that are present in the graph and come back to the same source vertex with the minimum cost. That is what the traveling salesperson problem is being involved. That is, a traveler needs to visit all the cities from a list of these cities which are present, basically which are represented by the given graph G, which contains a set of vertices and as well as set of the edges, where the distances between all the cities are known. The cities of all the, the edges, which are being concerned as the edges, are known, and each city should be visited just once. Each city should be visited just once, and to find what is the shortest path route, that the person visits each city exactly once and returns to the origin city is the problem of traveling salesperson. So if you go back to the what is actually the dynamic programming and how it gets differed with the case of the greedy approach. So dynamic programming, it is the there are two parameters which are involved whenever you consider a certain kind of the problem, which can be solved using the dynamic programming. That is optimal substructure and as well as the overlapping subproblems. So if you need to solve a problem which uses the concept of the dynamic programming, in such cases, two parameters are being involved. That is optimal substructure. An optimal solution to a problem contains optimal solutions to the subproblems. That is, in a particular scenario, if you found an optimal solution at a particular stage, that is the problems that can be solved using the dynamic programming, that is multi-stage graph problem, string editing, 0 or 1 knapsack using the dynamic programming, and as well as the traveling salesperson, optimal binary search trees, that is optimal cost binary search trees. So these are some of the example programs that can be solved using the dynamic programming. And when considered about the optimal substructure, take for example, that is a multi-stage graph problem. So within the multi-stage graph problem, you will be finding the solution, that is the optimal solution at each stage, which leads to the solution to the main problem. That is the optimal substructure. And overlapping subproblems, that is a recursive solution that contains a small number of distinct subproblems, which may be repeated several number of the times. As we have seen the same example related to the Fibonacci series. In the Fibonacci series, you can find, that is the formula to find the Fibonacci series, which has been given by Fibonacci of n is equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2. So here, if you need to find something like Fibonacci of 4, then in such cases, you should also find, that is Fibonacci of 3 plus Fibonacci of 2. And ultimately, within, if you need to find Fibonacci of 3, you need to find Fibonacci of 2 plus Fibonacci of 1, and so on. So once you found the solution to the subproblem, which is an optimal solution, then instead of calculating once again or formulating what is the solution to such subproblem which we have already found, just replace the respective values. That is the overlapping subproblems. And coming to the greedy method, that is, it is mainly the optimization problem, which have the simple subproblems similar to the original problem. That is, we have seen about the greedy method, that is knapsack problem. And within the knapsack problem, that is the fractional parts can also be taken. That is the 0 or knapsack using the greedy approach, where we can also break into the portions. But unlike in the case of the 0 or 1 knapsack, using the dynamic programming, either you can pick up that kind of the item or drop that kind of the item. So basically it chooses the solution optimally, that is locally, using the greedy method. That is optimal solutions can be found and which may lead to which are local. That is the local, if you consider the sub problem, and you'll be finding the optimal solutions which is to the local. And you can find the global solution by using such optimal solutions which are being obtained locally. And in the dynamic programming, all the feasible solutions are generated, while in the greedy, we are bound to the initial choice. And coming to what is actually the problem of the traveling salesperson, that is, a traveler needs to visit all the cities from the given list, where the distances between all the cities are known, and each city should be exactly visited once. And to find what is the shortest possible route that the person visits each city exactly once and returns to the origin city is the problem of the traveling salesperson. That is, if you look at an example of the traveling salesperson, like take for example here the given graph, like some city like C1, and which can be connected to the C2, and which can be connected to the C3, and similarly C4, and then C5. In between we have something like our C6 and so on. Consider. Then in such cases, the edges and as well as the costs are being associated. We have to visit starting from the source vertex. Starting from the source vertex, visit all the vertices, and then come back to the source vertex. That is the problem of the traveling salesperson. You cannot visit more than once in the traveling salesperson problem. And similarly, you need to find what is the shortest path. So traveling salesperson problem is one of the popular computation problem. We can use the brute force approach to evaluate every possible tour and select the best one out of the solutions. And for given n number of the vertices in the graph, there are n-1 number of such possible solutions using the brute force method. And instead of using the brute force method, as we are aware, what is the disadvantage of using the brute force method? So instead of the brute force method, and use the concept of the dynamic approach. Why we need to go for the dynamic approach? Because it also solves the problem of overlapping subproblem and as well as the optimal substructure. That is, the solution can be obtained in lesser time as compared with the brute force method through, take for example, if you need to solve the brute force method, it may take the linear time, and by using the dynamic programming, or it can also take the exponential time in using the brute force method. So you have to reduce this kind of the exponential time into some kind of the polynomial time. And using this kind of the dynamic programming, we can reduce from the exponential time into the polynomial time. That is the purpose where the dynamic programming concept is being involved. And consider the graph G equal to V comma E in the traveling salesperson problem, where V indicates that is set of cities, and E is the set of the edges, that is weighted edges where the cost has been associated, that is a distance or cost. And an edge E of U comma V represents the vertices U and V which are connected. And the distance between vertex U and V is being given as D of U comma V, the distance. Or we can also say W of U comma V, which indicates the weight. And basically, the edges which are being provided should be non-negative. And suppose we have started at city 1. Consider we are starting at city 1. And after visiting some cities, now we are in something like city J, consider. Hence, this is a particular tour, and we certainly need to know the city J. Since this will be determine which cities are the most convenient to visit the next city. And we also need to know all the cities visited so far and what we have not yet visited the city. So here, when you consider about the traveling salesperson problem, so given the list of the cities and the distances and the cost, that is the distance value is being provided. And similarly, you need to start from the source city and you need to exactly return. visit the other cities exactly once, and then come back to the source vertex. So what is the objective of the traveling salesperson? The objective is to find the shortest route that visits all the vertices in the graph exactly once and come back to the source vertex. And assuming that the graph is complete, that is, there is a direct edge between every pair of the vertices in both the directions, and that the weight of the edge u comma v is denoted by, that is, a w of u comma v, that is weight. And what are the applications of the dynamic programming? The applications of the dynamic programming involves such as to find the school bus route, and similarly it can also be used in terms of the welding, that is automated robotic welding in the automotive industry, and printed circuit board drilling and the laser cutting of integrated circuits. And similarly, the applications can also involve in the genome sequencing. What if you need to find start from the particular genome, and if you need to extract some kind of the sequence, then in such cases the traveling salesperson solution of this problem can be used in the human genome sequencing. And actually the problem of the traveling salesperson can be denoted by, that is, let g equal to v comma e be the directed graph with the edge cost which is being provided by c of ij, and the c of ij is defined such that c of ij is greater than 0 for all i and j, and c of ij is set as infinity if there does not exist the edge between I comma j. And a tour of g, that is a graph, there is a directed simple cycle that includes every vertex in v. That includes every vertex in v. The cost of the tour is the sum of the cost of the edges. That is, like take for example city 1 to city 2, the edge cost is something like 2, and city 2 to city 3, the edge cost is 4, and whatever the path that has been chosen using the dynamic programming concept, where exactly you are visiting the city once and then come back to the source vertex. Whatever the sum that has been associated, sum of all these kinds of the edge cost, that is what the problem of the traveling salesperson solution. The traveling salesperson problem is to find a tour of minimum cost. The tour is to be a simple path that starts and ends at the vertex 1 or city 1. Let g of I comma s be the length of the shortest path starting from vertex I and going through all the vertices in S and terminating at vertex 1 or city 1. The function, that is g of 1 comma v minus 1, is the length of an optimal salesperson tour, and of using the optimality principle, that is g of 1 comma v minus 1, you are subtracting, you're excluding city 1 or vertex 1 from the remaining vertices which are present. That is, if you consider g of 1 comma v minus 1, how can we understand? That is, you are starting from the city 1 or vertex 1 and excluding this city 1, what are the other remaining vertices or cities present? That will be the set of the vertices in the capital V, which has been given by minimum of c of 1k plus g of k comma v minus 1k, where k ranges between 2 to n. And generalizing the above function, then we can obtain the general formula of g of I comma s, which is a function which has been given by minimum of c of ij plus g of j minus s minus j, because we have already included the j vertex, and where j belongs to the solution, that is s. So assume the problem of the traveling salesperson. Here you can observe there are 4 vertices or 4 cities, that is city 1, city 2, city 3, and similarly city 4, and the edge cost are also been associated, that is from city 1 to city 2, city 1 to city 3, and similarly city 2 to city 4. There are various kinds of the edges along with the the cost is being associated. And how to solve this kind of the problem using the traveling salesperson problem? That is, the first thing is you need to find the cost adjacency matrix, because this is a graph that has been provided and you have to convert this into the cost adjacency matrix. So when you consider about the cost adjacency matrix, that is 0 to 0, that will be equal to 0, and similarly 0 to 1. This is like take for example city 1 to 3, 4. One, two, three, four. 1, 2, 3, 4, which indicates the vertices which are present. So 1 to 1 it is kept as 0, 1 to 2 because the cost is equal to 10, 1 to 3. So 1 to 3 with the cost to be equal to 15, 1 to 4. So from 1 we can reach to 4 with the cost to be equal to 20. In the same fashion, that is 2 to 1 is equal to 5, 2 to 2 0, and 2 to 3 which is equal to 9, 2 to 4 which is equal to 10. So 3 to 1 that is 6, 3 to 2 13, 0, and if you look at the 3 to 4 which is equal to 12, 4 to 1 which is 8, 4 to 2 which is equal to 8, 4 to 3 9, and 4 to 4 that is source city, I mean cost of I comma j, where I equal to j you can set to 0. So these are the values which have been associated with the case of the cost adjacency matrix. And to the next step, after finding the cost adjacency matrix, then based upon the formula, the formulas which have been given, that is a function, that is g of 1 comma v minus 1 is given as, that is minimum of c1k plus g of k comma v minus 1 comma k. And the next one, that is when you take the general term of your the function g of I comma s, which is been given by minimum of c of ij plus g of j comma exclude that kind of your the vertex, that is j, because we have included the j vertex and you have to exclude that kind of your the vertex into the remaining part. And coming to the initial, that is g of I comma null equal to ci1, where I ranges between 1 to n. So these are the formulas or the functions which are being used to compute the traveling salesperson problem using the dynamic programming. So coming to this one, that is the same thing, that is g of 1 comma v minus 1, we are excluding the vertex 1 from the remaining vertices, which is been given by minimum of c of 1k plus g of k comma v minus 1k, where k ranges between 2 to n. And in general, g of I comma s is been given as minimum of c of ij plus g of j comma s minus j, where j belongs to the set, that is solution. So g of I comma pi is given as ci1, where I ranges between 1 to n. So given certain kind of the the graph, we have converted this into the cost adjacency matrix, and similarly the formulas which are being denoted is also been provided. And the next one, you need to start from the source city, that is g of 1 comma pi, because we do not know what will be the next kind of the tour that has to be taken from the city 1. So here according to the formula which is been given, that is what is the formula that has to be used, that is g of I comma null is given as, that is if you look at the formula, that is ci1, where I ranges between 1 to n. So replace the same thing, that is ci. What is the value of your I? That is 1, that is c11. And what is the cost? If you look at the cost adjacency matrix, that is 1 to 1, which is set to 0. So in the same fashion, whatever the number of the vertices that are being present. So the next step that you need to find is, if you take g2 comma pi, which is been given as c21. So c21, what is the edge cost from 2 to 1? That is 2 to 1 with the edge cost to be equal to 5, the second line. In the same fashion, find g of 3 comma pi, that is which is being given as c of 3 1, and edge from 3 to 1, that is 3 to 1, which is given as 6. And the next one, that is g of 4 comma pi, which is given as c41, that is equal to 8. So far we have found out these kinds of the values. And the next thing that you have to consider is nothing but g of I comma yes. That is, if you exclude this kind of your the vertex from 1, what are the various kinds of your the vertices that can be reached? That is, out of these, what is the minimum? The minimum is equal to 2. So if you consider the next step, that is by excluding 1, what after you exclude the one vertex, then you need to find, that is g of 2. From 2 we can reach to 3, and similarly g of from 2 we can reach to 4, and similarly g of from 3 we can also reach to 2, and from 3 we can reach to 4, and from 4 we can reach to 2, and from 4 we can reach to 3. And so in the next stage you'll be finding the values of these paths. So in the same fashion you'll be finding, so how to find g of 2 comma 3, that is cost adjacency matrix is being provided, and then you'll be finding g of 1 comma pi, 2 comma pi, 3 comma 5, and so on. And you need to find g of I comma yes, that is you have taken from the city 1, that is the first step, and from the remaining step, that is minimum of c of ij plus g of j comma s minus j, that is you'll be finding g of 2 comma 3. So according to the formula, that is C23, I value is equal to 2 and similarly j value is equal to 3, because we are considering that kind of your the vertex, that is 3, plus g of j comma s minus j, because when you subtract this kind of your the s minus j, nothing will be present, and that is the purpose where C23 plus g of 3 comma pi is given as, that is C23, if you look at the cost adjacency matrix, that is 9, plus g of 3 comma pi, where we have already calculated, which is equal to 6. So 9 plus 6, that will be equal to 15. Similarly, g of 2 comma 4, where you get the value to be equal to 18, g of 3 comma 2, where you get the value to be equal to 18. Similarly, g of 3 comma 4, 20, g of 4 comma 2, g of 4 comma 3, with the values, that is 13 and 15 are being obtained. And the next step that you have to do is nothing but after finding, that is consider there are 4 vertices which are present, and so far the cost adjacency matrix and g of I comma s is been found initially, and from 2, what are the various vertices that can be connected? That is from 2 we can connect to 3, 4, and you find the minimum. That is, if you substitute the value minimum of Cij plus g of j minus sj, that is I value is equal to 2 in the first part. When you consider 3, that is I value is equal to 2, j value is equal to 3, and in the next part, that is take 4, that is j of 2, 4. From 2 we can reach to 3, from 2 we can reach to 4, and substitute the remaining values in your formula, that is plus g of j minus s minus j, that is C23 plus g of 3. What is the value of your the j? That is equal to 3. So g of 3 comma, if you exclude that one, that is the remaining vertex that is present is equal to 4. So g of 3, 4 comma, the second part is C ij, I value is equal to 3, I value is equal to 2, and j value that you are considering is 4. You are finding the minimum between these two, and then plus g of 4, because j value is equal to 4, then after exclude this one, the remaining vertex that will be present will be equal to 3, and the minimum of, you know the value of your the c of 2, 3 which you have computed in your if you consider the c of 2, 3, that is c of 2, 3 is equal to 9, plus already we have found g of 3 comma 4 with the value to be equal to 20, and the other value, that is 10 plus 15, that will be equal to 25. And in this fashion you'll be finding g of 3 comma 2, 4, g of 4 comma 2, 3, where you get the values, that is 25 and similarly 23. And in the next case you'll be finding g of from 1, what is the shortest path that can be reached to the other vertices, that is g of 1 comma v minus 1, that is from 1 and excluding 1, what are the remaining vertices that are being present, and what is the shortest distance which is being given by, that is there are 3 parts that you can consider, that is from 1 we can reach to 2, that is C12, from 1 we can reach to 3, that is C13, from 1 we can also reach to 4, that is equal to C14, and the remaining parts that are being present, that is g of 2 comma 3, 4, and similarly g of the depending upon the value of here the j, and exclude that kind of here the j into the solution. And similarly, where you get the minimum equal to, that is 35, 40, and similarly 43. Between this, the minimum is equal to 35, and that is how you have obtained what is the minimum cost tour. So the minimum cost tour is equal to, that is 35. You know the solution, and you need to find what is the path that has to be taken, because ultimately, even if you consider the same kind of the dynamic programming concept using the string editing distance, that is something like x equal to, there are certain number of the characters, that is 5 characters are being present, and y equal to certain number of the characters are being present, the length, that is equal to 4. Then depending, if you consider the x contains n number of the letters, and y contains m number of the length equal to m, then in such cases cost of n comma m provides information about what is the cost, minimum edit cost in the problem of string editing. In the same fashion, that is even in this kind of here the solution, that is traveling salesperson problem, you got the minimum cost to be equal to 35. And if you consider the string editing distance problem, if you need to find what is the the path that took what are the operations that are to be performed, then you need to trace back using this kind of here the formulas. In the same fashion, if you need to find what is the path that has been led to the minimum cost, so between these, that is between the 35, 40, and similarly 43, what is the minimum? Minimum is equal to 35. And which part has led to the 35? That is the first part, that is C12 plus G of 2 comma etc. So observe this kind of here the cost, that is C1 to 2, 1, 2. That indicates the path from 1 to, that is vertex 1 to vertex 2. And within the next case, that is G of 2 comma 3, 4. Observe what is the minimum. G of 2 comma 3, 4, the minimum. What is the minimum between? That is 29 and similarly 25. So 25 is minimum. And which part has led to the minimum? That is C24 plus G of 4 comma 3. C24. That is the path is to be established from 2 to 4. And similarly, observe the other part plus G of 4 comma 3. So G of 4 comma 3. And what is the minimum in G of 4 comma 3? So go back to the formula, that is G of 4 comma 3 is given as C43 plus G of 3 comma pi, that is equal to 15. So what is the path? That is 4 to 3. So 4 to 3 is being established. And if you consider the other one, that is G of 3 comma pi. So when you consider G of 3 comma pi, that is C3 to 1. So C31. So the path has to be established from 3 to 1. This is how we can solve the problem of the traveling salesperson using the dynamic programming concept. So far, if you recall about the concept of the dynamic programming, the traveling salesperson problem, we need to start from the source vertex and visit exactly each vertex once and come back to the source vertex. And similarly, if you consider about the shortest tour, what is the problem of the traveling salesperson problem? That is, you need to find the shortest tour starting from the city 1 and exactly reach to the source vertex. And whichever is the tour is the shortest path, that will be the solution for the traveling salesperson problem. And we got the minimum value, that is 35, and we have traced back. That is between, what is the minimum between 35, 40, 43, 35 is the minimum. And which part has led to the 35, minimum value, that is C12. We have established the path from 1 to 2 and observe the remaining part, that is G234. And within your G234, 2 comma 3, 4, what is the part that has led to the minimum? That is 25. And which part? That is C24. So we have established the path from 2 to 4. And similarly, a G of 4 comma 3. Observe the formula of C of 4 comma 3 and what is the cost that has been associated and its respective path, that is 4, 3. So 4 to 3, the connection is edge has been connected. And similarly, G of 3 comma pi, that is if you look at G of 3 comma pi, which is given as G of C31. So the path has been established from 3 to 1. This leads to the minimum solution with the minimum cost to be equal to 35. This is how we can solve the problem of the traveling salesperson using the dynamic programming concept.